All right, hello everyone. Welcome to exam review 6. This is the last exam before the final, so everybody give yourselves a round of applause. We're almost there. So this exam is all about ethers, alcohols, epoxides, thiols, and sulfides. Essentially anything that has an oxygen or a sulfur in it, whether that be an OH, such as with alcohol, an SH in thiols, an oxygen between two carbons, which is an ether, or a sulfur between two carbons, which is a sulfide. But those are generally what we're going to be going over today. And I'm first going to talk about alcohols, then we'll talk about ethers and crown ethers, followed by epoxides, followed by thiols and sulfides. Okay, so let's first talk about what an alcohol is. So you may recall that an alcohol is essentially any carbon chain, anything with carbon in it, that includes an OH group, also called a hydroxy group. It's called hydroxy because we have a hydrogen and an oxygen group. And this hydroxy group can be primary, secondary, or tertiary, just like when we talked about alkyl halides. So like, for example, here, we can see that this one is going to be a primary alcohol because the OH is attached to a primary carbon. If we had something like this, then this would be a secondary alcohol because our OH group is attached to a secondary carbon. And finally, this would be a tertiary alcohol because it's attached to a tertiary carbon. And so there are different reactions that each one of these can go through, but I first wanted to sort of show the difference between primary, secondary, and tertiary. All right. So making alcohols is pretty easy. We've been doing it since, I think, chapter 3, because that just includes a substitution reaction. So let's say we have something like this. We have Br right here. And we're going to treat our nucleophile as OH negative. And this will be an SN2 reaction because of a primary alkyl halide and a strong nucleophile. The strong nucleophile being OH. So essentially all that's going to happen, the oxygen, let me draw the arrow a little bit better. The oxygen replaces the bromine on that carbon chain, and we end up with our alcohol. All right? Okay. So let's go on and talk a little bit about the physical properties of alcohols, like what makes alcohol special when compared to something like an alkyl halide. So every single molecule has intramolecular forces. So if you remember from Gen Chem, there are 3 main ones that we will be talking about in this class in Organic Chemistry 1. The first one is going to be Van der Waals, and I will be referencing that as VDW. We'll be talking about dipole-dipole, which again, I will designate as DD. And then finally, we have hydrogen bonding. You may remember these from Gen Chem, but I'm going to briefly go over each of them and what they mean. 1, because they're important to remember, and 2, they have a lot to do with some of the physical properties of alcohols. So first off, van der Waals. Everything will have van der Waals. And van der Waals is also called London dispersion or dispersion forces. They're the same thing, or well, they're not exactly the same thing, but when referencing intramolecular forces, they're usually regarded as same or very similar things. So what is van der Waals? What is dispersion? So everything will have some sort of electron cloud. Let's take 2 carbons right here. So 2 carbons bound together, each one of them is going to have some sort of like electron cloud. And that electron cloud, that's not what to do. That electron cloud is basically going to make up that carbon-carbon bond. And so let's just treat that carbon-carbon bond as 2 electrons. And so these electrons are always going to be moving around. They're always going to keep the bond, but they're always going to be moving around slightly. So at some points, those electrons could be closer to the left or the right carbon and make it slightly negative and make this one slightly positive. or they can be around the other carbon, making that one slightly negative and this one slightly positive. This just happens randomly. The electrons are dispersed randomly. That's where the word dispersion comes from in this case. And so just at random points, we could either be in this state or this state, which causes attraction between two different of the same molecules. And thus everything has van der Waals, everything has London dispersion. So a few examples would be a carbon chain like this has van der Waals, a carbon chain like this with an alcohol. The alcohol has London dispersion, van der Waals forces, and then something like this, an ether, also has van der Waals forces. Again, we'll go over ethers a little bit later. I'm just using this here to show you how each one of these has van der Waals. Okay. So dipole-dipole essentially is talking about polar bonds. So when we talk about polar bonds, for example, carbon to oxygen, we know that oxygen is going to be slightly negative because it is more electronegative than the carbon. So it's pulling all the electrons towards itself and thus will be slightly negative, and this carbon will be slightly positive. So this dipole-dipole force, it is always there. Whereas the van der Waals forces, it's there in an instant and then gone in the next because of the movement of electrons. The dipole-dipole force will always be present, thus it will generally be stronger than the van der Waals force just because it's always there. And again, to have dipole-dipole, you will have a polar bond. So from these three up here, the ones that have dipole-dipole are the ether and this one right here. And yes, you may think, oh, but this one's symmetrical. So overall, it's nonpolar, but it still has polar bonds, which make it have that dipole-dipole force. Okay, so the last and final one is going to be hydrogen bonding. And this one's probably going to be pretty obvious. If you have a hydrogen bond, then you're going to have hydrogen bonding. But again, these hydrogen bonds must be between specific atoms. So oxygen and hydrogen, nitrogen and hydrogen, and fluorine and hydrogen. In this class, at least when we're talking about alcohols, obviously the one that's most important will be these OH bonds. So finally, we can see that the only one with hydrogen bonding will be that alcohol right there. And so the way that I've arranged them from weakest being van der Waals to strongest being hydrogen bonding. So we can see here that the regular carbohydrate, that one has the weakest intramolecular forces, followed by the ether, followed finally by the alcohol group. Okay? So why are we even talking about this? Well, we're talking about this because we want to talk about the physical properties, specifically the boiling point. So the boiling point of a specific structure is going to be tied directly to its intramolecular forces. The stronger the intramolecular forces, the stronger these atoms are going to hold on to each other. The less likely they're going to want to be separated through boiling. So the stronger your intramolecular forces, the higher your boiling point. So these numbers are not going to be accurate. I'm just going to show you sort of like a represented example. So let's say that the alcohol boils at 100 degrees Celsius. The ether may boil at 80 degrees Celsius. And then finally, that regular carbohydrate, that might boil at 40 degrees Celsius. So you can see here that with the decreasing intermolecular forces, the decreasing boiling point, okay? And so that's where the idea of the physical properties, as in the boiling points, will come in. Does that make sense to everybody? Does anybody have any questions about that? If not, there's one more big physical property I kind of want to talk about, and that's going to be solubility. Oh, sorry, before we move on to that, I want to say one more thing about van der Waals forces. So the bigger your molecule, the more prominent your van der Waals forces, because there's more surface area for those electrons to go to. There's a more polarizing space that they can create. So the bigger the molecule, the more van der Waals force. So like for example, this 4-carbon chain and then this 1, 2, 3, 4, 5, 6, this 6-carbon chain. The 6-carbon chain will have stronger van der Waals forces because it's bigger, because it has more surface area. So it will have a higher boiling point than the 4-carbon one. So like this could boil at, I don't know, 30 degrees Celsius. This one might boil at 20 degrees Celsius. So you can see here that the higher the surface area, the more the van der Waals, and the higher the boiling point. Okay? All right, so I'm going to clear this. And now we're going to quickly talk about solubility. So let's compare something like this to something like this. All right, if I were to ask you which one do you think is soluble in water, which one will you say? And you can answer this silently. You can answer this on your piece of paper. Which one do you think will be soluble? A or B? Well, if we think about this for a second, let's compare these to H2O. So H2O is going to be more similar to B because B is smaller. It's going to be more similar to water, so it's going to be soluble in that water. And the general rule of thumb is that for every 1 oxygen, you have to have 5 carbons to be soluble. So for example, this one here has 1, 2, 3, 4, 5, 6, 7 carbons and 1 oxygens. So this is insoluble in water. Insoluble, okay, I spelled it right. Whereas this one over here, it has 2 carbons for its 1 oxygen, so it is soluble in water. If you continue to add on oxygens, you can increase your solubility or increase how many carbons you can have. For example, if I added an OH over here, then we would have 2 oxygens for all of those carbons, and it would become soluble. So those solubility rules are pretty simple. It makes, yes, you need 5. So for every 1 oxygen to be soluble, you have to have 5 or less carbons. Like for example, this one over here has 2 carbons for its 1 oxygen. And so the general rule here is that when you have polarity, you're dissolvable in water. So polar dissolves polar in that oxygen, or H2O, is going to be obviously a polar molecule. That oxygen will be partially negative. I actually wrote positive there, but it will be partially negative, and the hydrogens will be partially positive. When you have oxygen, oxygen is of course going to be a polar molecule. And so it's going to pull negative charges towards itself. But the problem is once it gets to about 5 carbons, it cannot pull all of those positive charges towards itself. It kind of fades, and then that portion becomes insoluble. And that's why we have hydrophilic heads and hydrophobic tails for lipids in our plasma membrane. Again, you don't need to know that for this test, but calling back to stuff you talked about in biology, this might make it help make a little bit more sense. I used make like 5 times in that sentence. Does anybody have any questions on that? Solubility rules? No? All right. So those are the 2 big physical properties you should know. Yes, you do follow the ratio. So if you have 5 carbons, then you should be soluble. 5 carbons is sort of like the borderline soluble. So most of the time, they'll either give you more carbons, like 6 carbons, or less, like 4 carbons. But if you do have 5 carbons and 1 oxygen, technically it is still soluble. All right. So those are the 2 big physical properties we need to talk about as far as oxygen alcohols go. Okay. So let's talk a little bit about the nomenclature. Again, I'm going to sort of breeze over nomenclature because I feel like that's the easiest to find sort of a walkthrough on. So let's say that we have just a regular alcohol like this. Like every single other nomenclature, you're going to first want to find the parent chain. Obviously, that's going to be this one right here. And what's important with alcohols is the parent chain has to include the carbon that has the OH group. So for example, if we had something like this right here, we have something like this right here. We would have, so if we have something like this, we would call the parent chain this carbon chain right here instead of this one right here, because we want the carbon chain that includes the OH group, okay? So we'll name both of these, but first let's start with this more simple first one. So obviously here's our parent chain, 1, 2, 3, 4. So our base parent name is going to be what? It's going to be butane. Okay, so this is our base parent name. And so then we say, okay, we have this group here, this OH group. OH group is going to change the name by changing this E into an OL. So we become butanol. So that's how we change the name. We also have to designate where the alcohol is, where that OH group is. And I know some of you may be saying, well, if it's on 1, we don't have to say 1-butanol, do we? Yes, when it's in this linear form, you have to tell us which carbon it is on. The only real time that you're going to drop that 1 is if we're in some sort of cyclic molecule like this. Then and only then can we drop the 1. Personally, I usually always keep the 1 in the name just because it helps me keep track of everything and there's less room for error just in general. So there are 2 ways we can designate 1-butanol here. We can either say 1-butanol, just putting it in front of the parent name, or butan 1-ol. Most of you are probably going to prefer this top one here, but personally, I really like this bottom one because what it does, it keeps the 1 with the substituent. It's like when we say 1-methanol butane or not methanol, 1-methyl butane or something. We're keeping that number with the substituent. That's why I personally like this bottom one here, but both of them are right. You'll just probably see me using this bottom version more because that's what I prefer. All right? Okay. So let's look at this other one right here with the pink. So obviously we're gonna write down our parent name, which is gonna be 1, 2, 3, 4 once again. So that's gonna be butane again. And once more, we're gonna change the E into an OL and we become butanol. Okay, so now we have to number it. Here, I've numbered it the opposite way. So we see here, and yes, I'm going to get into naming with a double bond and an alcohol, but you can see here that, again, we're going to want to put our substituents on the lowest number possible. So it's going to go 1, 2, 3, 4, where alcohol is on 1. And for the record, if you have 2 functional groups, in general, you're going to want to put the OH on the lower number, okay? So here, of course, we have this group right here. So that'd be 2-ethyl butan 1-ol, or 2-ethyl 1-butanol. But again, I personally prefer this one. Both of them are technically correct. So that's in general how you name an alcohol. So one question that I just got was, how do we name an alcohol that has another functional group, like a double bond? So let's do that very quickly. We'll do a generally simple example. So let's say we have something like this. So we have a double bond and an OH group. You're going to want to put both of these on the parent chain if you can. If it's impossible, then you'll put the OH on the parent name. But I don't expect that you may run into a problem like that. Just in general, put both the double bond and the OH on the parent chain. Here it's easy because it's just this. All right, so we say we have 1, 2, 3, 4, 5, 6. So that base name is going to be hexane. So what's important here is to say I have 2 separate functional groups that are going to change this base name. the OH right here is going to turn this into hexanol, whereas this double bond right here would turn it into hexene. So let's write down both of these. So if I say hex and all for the alcohol and hexene for the double bond. So what's interesting here, somebody said, what if there was a methyl or an ethyl group on the first carbon as well as an OH? So if there was like a methyl right here, then you would just say there's a methyl. You would just name it as per usual. The only big difference is there might be stereochemistry, which I haven't drawn in. Anyways, back to this. So we can see that the double bond and the OH group, the hydroxy group, they change different parts of the name. So all we really have to do is sort of smash the two of them together into hexene. So you can see here, now changing that last part of the name turns it into hexenol. Okay, everybody with me so far? So again, we're going to go ahead and number it in order to give everything the lowest number possible, specifically give the OH group the lowest number possible. 1, 2, 3, 4, 5, 6. So we know that our OL will be on 2. So I'm going to say 2 OH, and our double bond will be on 3. 3 for the double bond. Just writing those down to make sure that I'm keeping track of them. Okay. So now there are a few different ways you can go about naming this. You could say hex 3 ene 2 all. You in a situation like this, in most situations, you're going to prioritize the OH over the double bond. You want to give the OH the lowest number possible. So this is one way to name it. We could also name it something like 3-hexene 2 all. But what's important here is we can't put both of these numbers in front of the hex, because that makes things confusing, because you won't know which one is on 2 and which one is on 3. Again, I personally prefer this way of naming, but this one should be okay as well. All right, so that's generally how you name alcohols. Any questions? So let's use that question that we had earlier. So like, for example, what if we had an ethyl or a methyl group right here? Well, what we'd have to do is we would say, okay, now I have a 2-methyl hex 3-ene 2 all, but I'm not quite done because I also have to assign stereochemistry. Well, that's pretty easy for this one, just because our OH is on a solid wedge and our lowest priority will be, oops, I messed up. Let's turn this into an ethyl group, because if that was a methyl group, then we wouldn't actually have a stereogenic center. So just bear with me. So we can see here that we have OH on 1, this group here on 2, this on 3, and then our methyl group on 4. If you need review with the stereochemistry rules, then I would advise you to go and rewatch my review video that covers that. Okay, so anyways, so we see here our lowest priority is not on our dashed wedge. So we have to go ahead and redraw it. I'm running out of room, so I'm just going to draw it over here. Oops, let me draw it in black. So we're going to redraw our stereogenic center. Our 4 group will be on top. Our 2 group will be right here, our 1 here, and our 3 here. And all we're going to do is we're going to grab it by 2. We're going to grab it right here, and we're going to twist it around to put 4 where 3 is, 3 where 1 is, 1 where 4 is. So we end up with this. 4 is now on the dashed wedge, 1 is up here, 3 is right here, and 2 is right here. And then we do our stereochemistry. And we say, okay, this is going to be S2-methyl hex 3, or 2-ethyl, not methyl. Hex 3-ene 2 all. And yes, there would also be an EZ for this double bond right here. This one obviously would be Z. No, wait, sorry, E. Sorry, I always mix up E and Z. I have to go through the Z, Zame, Zide in my head, or I mix them up. So this would be S, E, 2, or it would be like, actually, I'm not sure which one comes first, whether it be S or it be E. Usually you won't have to define those in the same name. But if we were doing the E, it would just say E2 or E-2 ethyl -3 E-2 all. Somebody said if there is no given wedge or dash, there is no stereochemistry. Exactly. If they don't give you the wedge or the dash, you can't know the stereochemistry. And if you write down any stereochemistry, you're opening yourself up to be wrong. Okay. So I'm going to clear this because I think we've got over naming enough, because naming, again, I feel like is the easiest thing to look up if you're having trouble with it, but I did want to go over it quickly because some people were having some issues with it. Okay. So now we're going to get up into the actual reactions. We're actually going to talk about alcohols. We already talked about how to create an alcohol just through a substitution reaction where we replace it using either SN1 or SN2. So this would be SN2. We can also use SN1. So if we have something that's very substituted and we use a weak nucleophile like water, we can still replace it by first creating our carbocation, then adding our nucleophile, and then deprotonating, and we end up with our alcohol. So just by doing a replacement reaction, a substitution reaction, however you want to call it, we can create an alcohol. We've been doing it since the very beginning. Are there any questions with that? If not, we can also talk about how we can also make alcohols from double bonds. So if we hydrate it, so if we hydrate using an acid, so I'm going to say H2SO4, we will make first a carbocation and then add on our OH. If we use hydroboration oxidation, so I'm just going to put HBO for hydroboration oxidation, we will add anti-Markovnikov and we create the opposite alcohol. Okay? So these are the main ways we can make alcohols. And you may be saying, but Casey, what about triple bonds? We can hydrate those, can't we? While yes, you can hydrate triple bonds, most of the time that is going to create either a ketone or an aldehyde. So if we do H2SO4 with acid catalyzed hydration, we would end up with a ketone. If we do hydroboration oxidation, so I'm going to write HB over here, then we would end up with an aldehyde. Okay, so that's why we generally don't really talk about the hydration with a triple bond, acid catalyzed hydration, and then I've already labeled hydroboration oxidation. So again, that's why we generally don't talk about triple bonds when we're trying to make alcohols, because they don't make alcohols. They will either make an enol or more likely a ketone or an aldehyde. And that's why most of the time you're going to see us want to make the alkene from the alkyne before we do our alcohol creating reaction. But these are the main ways, at least we know how to make alcohols. Are there any questions about that? Any questions, concerns? And yes, I did label each one of these. I hope I labeled them well. That acid is dilute. Yes, I mean, it doesn't really matter if you're using dilute H2SO4, but as long as it's there. It's just a lot of the time they say dilute H2SO4 because if you're in the lab and you're using very, very concentrated H2SO4, that's going to not be fun if you spill it anywhere. That's why it's usually going to be dilute. Okay? Are there any questions there? Are we all good? Okay. And so overall, that is how we are going to make alcohols in this class. Pretty easy, I hope, because a lot of it is sort of a review. So I hope you didn't get too tripped up on that. but I digress. So now let's talk about the actual reactions we can undergo when we have an alcohol. So let's say that we have an alcohol here that we're going to be doing a bunch of testing on. So with this, remember when we talked about how we can use a double bond and turn it into an alcohol? Well, we can do the exact opposite. We can transform an alcohol into a double bond by introducing it to an acid catalyst. So let's talk about this. So we have H2SO4 right here. And so now let's think about this for a second. A regular elimination, a regular substitution reaction, we need a good leaving group. OH on its own is not considered a good leaving group. So we need to change it somehow to turn it into one. Usually for our class, what we'll be doing to turn that oxygen into a good leaving group is adding on either another hydrogen or replacing that hydrogen with something else, which we'll talk about later. But for this acid catalyzed dehydration, we will be protonating it. We will be adding on that hydrogen. So we end up with OH2 plus. And then on the other hand, we end up with the conjugate base, OSO3 negative. This will come into play a little bit later. I'm just putting it off to the side for a second. Okay, so when we have this, now we have a good leaving group. So our leaving group is going to leave, and we are going to end up with a carbocation. Of course, we'll do whatever shifting we need to in order to make the more stable version of the carbocation, in this case, a 1,2 hydride shift, but overall, it won't really matter because what happens is our base, our conjugate base, like this one right here, will come in and grab the hydrogen off of one of the carbons, which then can allow it to do the full elimination reaction, and we end up with this double bond right here, okay? And so now we can do whatever reactions we want to with that double bond that we can do with double bonds. So we can go undergo halogenation, hydrohalogenation. We can even recreate an alcohol, but we can recreate it in a different spot. For example, if we wanted to do hydration using an acid, so I'm going to put hydration using A, we can see that to add Markovnikov, our OH will add right here, and we end up with a different type of alcohol. So that's why this dehydration is sort of an important step, an important thing to know in general, because we can make it turn into a double bond, which then can undergo all different sorts of reactions, even rehydration and putting that OH onto a different spot. Does anybody have any questions about this? Okay, awesome. Okay, so let's clear this. And so let's use that same exact guy right here. And so let's say that I've decided I want to replace that OH with a bromine. Again, OH is a really, really bad leaving group. So what we have to do is we have to protonate. So instead of using just regular Br or Br2, we have to use Hbr. Because that Hbr will first, oops, that's the wrong color. We'll first protonate the oxygen, we'll just roll with it, getting rid of that bromine, and we end up with OH2 plus and Br negative. And obviously what's going to happen is our nucleophile, the Br negative, will replace that OH2 group, and we just end up with an SN2 reaction with Br right there. Okay? Pretty easy, nothing too intense. It's just a different form of the same reaction that we're used to. And just to say, this is nucleophilic substitution. Okay? Okay. So nucleophilic substitution, easy. But sometimes we don't want to do this nucleophilic substitution. Okay, but sometimes you don't want to use HBr, HCl. You could do this with technically you could do this with any halogen. Sorry, I forgot the name for halogen. But sometimes you don't want to use HBr, you don't want to use HCl. We have special reagents that will undergo this substitution, but in a slightly different way with a slightly different mechanism. For bromine, we would use something called PBr3. And so let me quickly draw out PBr3. Sorry, my pen wasn't being registered. So it's important to us to know the mechanism of this. So PBr3 looks like this, where that phosphorus has a free pair of electrons. So what's going to happen here essentially is that phosphorus is sort of going to take the place of the hydrogen as before. So it'll grab onto the phosphorus, this bond will break and go onto the bromine, and we end up with this right here. Let me see if I can draw this nice and pretty. Oh, that should be a P, and then Br, and then that bromine will just come along and it will replace that OH, just like it did when we were talking about the nucleophilic substitution using HBr. It's just this is just using a different type of reaction, and you may want to use PBr3 for certain specific reasons, like maybe you want to do another reaction at the same time that HBr would interfere with, or anything of this sort. Just know that PBr3 essentially is going to replace the oxygen, the OH group. Okay? All right. So let's clear this. And so the other special reagent that we have to talk about is going to be SOCl3. And yes, generally, HBr and PBr3 will do the same thing with alcohols. Same thing with HCl and SOCl2, not 3, SOCl2. Okay? But with SOCl2, it's going to have basically the same sort of mechanism as far as the PBr3. Somebody said, does Br2 and light do anything to alcohols? Not necessarily. I mean, technically it could, but we usually save those radical reactions specifically for alkanes, specifically for carbons. Oops, my cat knocked something over, but it's fine. Anyways, so again, SOCl2 will generally do the same sort of mechanism as PBr3. Somebody said, could HBr work in SN1? So the problem with HBr with SN1, so like if we had OH, HBr right here, or if we had the triple bond, like if we had tertiary, then yes, technically HBr would have to go through SN1. But generally, the problem with using HBr in SN1 is that Br negative, which is what we get after we remove the hydrogen, that's a really strong nucleophile. So sometimes there's sort of issues with pairing it with SN1. So most of the time we'll see it with SN2. Same for HCl, same for HI, same for all the other ones. Except we usually don't see this reaction with HF because HF is really bad at dissociating. All right. Okay, so let me clear all of this. So again, SOCl2 works a lot like PBr3, where the oxygen will come in and grab the sulfur. This bond is going to break, however. The oxygen bond is going to break rather than the chlorine bond, and we end up with this. So again, let me hopefully draw this very prettily. O negative, O plus right here. This is using SOCl2 in our reaction. Okay. And so then what happens is going to be something similar to when we talked about Grignard's reagent. The chlorine is going to leave This oxygen is going to recreate its double bond with sulfur. And we end up with this. Which then can come along and essentially replace that positively charged oxygen. And we end up with that Cl replacing that OH right there. And what'll usually happen is a whole slew of reactions where this Cl ends up leaving, this hydrogen ends up leaving, and we end up with SO2 HCl instead of SO2ClH. It's just these two separately are more stable than this one together. I don't think you have to know that mechanism too well, but you do have to know sort of what's happening with this reaction here. And this reaction using SOCl2 is also going to be using pyridine as a solvent. So you'll usually see pyridine, let me hope I can spell it correctly, underneath the arrow as a solvent because it is a nonpolar solvent and it just sort of keeps everything overall stable. So whenever you see SOCl2, you're also mostly going to see pyridine. It's just the pyridine isn't what's super important in this reaction. Okay, so one last thing I want to talk about before getting into the next topic is POCl3. So you can see POCl3 looks a lot like SOCl2. The thing with POCl3 though is POCl3 is going to cause it to undergo dehydration. So it's basically going to be doing the dehydration of the using an acid. So we'll start with our OH group. We use POCl3 and we end up with a double bond. So what's important here is to always differentiate between POCl3 and SOCl2. I don't think POCl3 is going to be on your test because I don't think we go over it. It's not listed in the topics, but I did want to give you a note about it because if you go on to Orgo 2 and they start talking about POCl3, now you know that it's going to cause an alcohol to undergo dehydration. The way that I always remember these in my head, the SOCl2, the S stands for substitution, and the P stands for pulling the oxygen off. I don't know, just little funny ways to remember it. But again, I don't think you need to know this for your test, but you may need to know it for organic chemistry as a whole in the future. Okay? All right. So I think, let me go over the list. That is the first four. The first four. We'll talk about tosylate in a second. I just want to make sure everybody's with me so far on all of those different topics. Okay, glad to know we're on the same page. And so the last, not the last thing that we'll go over here, but the last thing we'll go over as far as alcohol reactions as a whole go are going to be converting OH into OTS. Ooh, scary. So let me clear this. So whenever we have OH, like every single time, somebody said, will we be able to do practice problems? Maybe. I will do my best to make sure we have time. Okay, so like we said before, we need to turn this OH into a good leaving group. The way that we did that before was by protonating it. But what if we can't protonate it? What if we don't have HBr? We don't have HCl. We have to do something else. Well, what we can do is we can use something called Tosyl Chlorate. You will usually see it written as TSCl. Okay? So what Tosyl Chlorate does is it's going to replace this hydrogen with that whole tosyl group. Okay? And I don't think you need to know the mechanism, but I will be showing you the overall structure of it. The overall structure of it is going to look something like this. Okay. And so we can also see here that it looks a lot, oops, sorry, I meant to erase that, not scribble over it. We can see that it looks a lot like when we did SOCl2. The only difference is that we have this phenol group right here along with this oxygen right here. But essentially what's going to happen is we are going to end up with OTS instead of OH. So we would end up with something that looks like OS and then this phenol group right here. Like this. And then we would also end up with HCl because that's essentially where the hydrogen in the chlorine went. The whole reason for having this OTS here is so now that OH is now a good leaving group. We can get rid of it. So what we can do is we can say, we can do any other reaction that we've done before. So we could do a replacement reaction, a substitution reaction, an elimination reaction, and more. Okay. Does that answer any questions about tosylate? Tosylate is just this whole group right here. And so, like, for example, what we can do is we can react it with OCH3 negative. And what will happen is that this whole group here will be replaced by that OCH3. Okay? Do we need to know the mechanism of attachment? I do not think so. The topics that he sent us in the email says you need to know converting alcohols to tosylate and how we can use that for substitution and elimination, and not necessarily for sorry, I forgot the word. Not necessarily the mechanism. So the big thing about TS that's different from SOCl2 or PBr3 is that we can use this whole group for anything. We could replace it with anything. So you can see here, we replaced it here using OCH3. Whereas if we used PBr3 or SOCl2, we would only replace it with Br or Cl respectively. That's the big thing with tosylate. We can also have it undergo elimination. So if I were to react this with tert butoxy or something like this, we could undergo elimination and end up with this. Okay? So that's why the TS is important. It's because we don't need any other specific reagents other than it. Okay? All right. So I think that is all for the reactions of alcohols. And now we're going to start talking about oxidation and reduction. All right. So now we're going to get into talking about oxidation and reduction. So in Gen Chem, we had a different definition for oxidation and reduction than we do in organic chemistry, but it actually is going to be very similar. So if you remember, oxidation in Gen Chem would be oxidation is the loss of electrons. So we minus electrons, we become more positive. For reduction, reduction is the gain of electrons. So we gain electrons, we become more negative. Okay? In organic chemistry, we have a slightly different definition, where oxidation is the increase in carbon X bonds, where X is anything that's generally electronegative, or a decrease in carbon hydrogen bonds. Same thing with reduction, but I guess the opposite thing with reduction. Reduction is the lessening of carbon X bonds or the increasing of carbon hydrogen bonds. Most of the times, these CX bonds will be oxygen, so that's what I'm going to be using for my examples. So let's start with two different carbons. And let's say that they're like basically transforming into each other. We have this carbon over here, carbon A, and this carbon over here, carbon B. Let's say that carbon A has an OH and carbon B has a hydrogen. So let's pause here. Oxygen is generally more electronegative than carbon. We all know this. We know that oxygen is more electronegative than carbon. So it's going to hog all the electrons. It's going to cause the carbon to be partially positive. So we're going to sort of give that an arbitrary number. For every carbon X bond, for every carbon bond with something that's more electronegative, we will say that that carbon is becoming more positive. We're going to say that carbon is gaining +1. Okay? If we look over here at carbon B, we can say the exact opposite. While usually, yes, we sort of tend to describe carbon-hydrogen bonds as nonpolar, when we're talking about oxidation reduction, all of that stuff, we're going to consider the carbon to be more electronegative than the hydrogen. So it's going to become more negative. It's going to become partially negative. So for every carbon hydrogen bond, we're going to say it's going to have a -1. This +1, -1, those are our oxidation states. And if you become more positive, so like if I go from -1 to +1, that's going to be oxidation. If I go more negative, I go from +1 to -1, that's going to be reduction. We're reducing the charge, okay? So we can see here, that is how the oxidation and reduction definitions from Gen Chem feed into organic chemistry, which feed into oxidation states in this class. So let's talk about a random carbon. Let's say we have a carbon right here that's attached to another carbon right here. Now, if I ask you the carbon oxidation state of this carbon, what you would do is you would say, okay, so I have +1 bond for one of these oxygen bonds. I have +1 bond for the other bond because we have a double bond. We have -1 for this hydrogen bond, and we have +0 because this carbon-carbon bond is not going to alter the oxidation state. So we have +1, +1, -1. Our oxidation state will be considered to be +1. And if I said, okay, what if I'm going from this guy here to this guy here? Is this oxidation or reduction? Well, if we look at our reduction rule, our oxidation reduction rules for organic chemistry, we see our carbon-hydrogen bonds went up from 1 to 2, and our carbon X bonds, or carbon oxygen bonds, went down. We went from 2 to 1. So obviously, this is going to be a reduction. And if we were to look at the oxidation states, we would say +1 for our one oxygen bond here, -1 for this hydrogen bond, -1 for this other hydrogen bond, +0 for this carbon bond, and we end up with +1, -1, -1. We end up with an oxidation state of -1. So we can see there, we went from +1 to -1. That is a difference from -2. So we reduced, okay? Does that make sense to everybody? Does anybody have any questions there?
I have a question.
Go ahead.
I'm just a little confused on like where the 1 is coming from. Like the +1, like the -1, like I'm just like lost.
Okay. So the +1 and the -1, those are coming from our carbon X bonds or carbon hydrogen bonds. So for example, we can see that we have one carbon oxygen bond here. That's going to be one of these +1s.
Oh.
Another carbon oxygen here. That'll be the other +1. Then we have a carbon hydrogen, which will be our -1. Okay?
Oh, nice. Okay, cool.
Okay, so that's where the +1s, the -1s are coming from. And we can see there that we go from +1 to -1. We're becoming more negative. That's going to be reduction. And we can also see its reduction by the organic chemistry definition because our carbon hydrogen bonds are going up and our carbon X bonds are going down. Carbon hydrogen bonds are considered -1 because we are sort of considering carbon to be more electronegative than hydrogen. Okay? Does that make sense to everybody?
Thank you.
No problem. Okay, we're going to do more sort of little examples, but I just want to make sure everybody knows what's going on here. A carbon-carbon bond is considered 0. So you can see like this +0 here. Let me find a different color. This +0 here is coming from this carbon-carbon bond. Okay. So let's do a few more examples in order to sort of make it seem more clear. So let's say that we have this here. We have H, OH, carbon, O, C, OH, O, and CO. So we are going to assign oxidation states for each one of these. Try to do it ahead of me if you can, but we will go over every single one together. So we know that CX bonds, C oxygen bonds in this case, we will give those bonds a number of, oops, turned on my camera, but anyways, we'll give these CX bonds a value of +1 because the carbon is becoming more positive because the X is pulling the negative charge away. So we're going to say that's going to be a +1 because it's becoming more positive. Carbon-hydrogen bonds, we will give a value of -1 because overall, at the very least, carbon has a very slightly more electronegative value. So it's pulling positive charge away from the hydrogen. So it's going to be partially negative. So we're going to say that's going to have a value of -1. Carbon-carbon bonds are exactly the same. They're pulling the exact same amount. So neither one is going to be more electron dense than the other. So we're going to say that's going to be 0. So let's start with this first one. So we can see it has 1 carbon-oxygen bond. So we're going to say that is going to be 1 + 1. It has 1, 2, 3 hydrogen bonds. So we're going to be saying that's going to be 1, 2, 3 -1s. And there are no carbon-carbon bonds, so we won't worry about that. We're going to say +1, -1, -1, -1. That's going to be -2. So this one has an oxidation state of -2. Let me highlight these with the color so you can see where all the numbers are coming from. Okay. So now let's look at this next one. We can see that it has 2 carbon-oxygen bonds. Each one of those double bonds counts as 1. So we're going to say +1, +1. Let me highlight that. And then we have 2 carbon-hydrogen bonds. So we're going to say -1, -1, which equals 0. So this one has an oxidation state of 0. Everything is sort of canceling out. Then we look at this next one here. We see 1, 2, 3 oxygen bonds. So we're going to have +1, +1, +1. And then we have 1 carbon-hydrogen bond. So that's going to be -1, which then equals +2. So the oxidation state here is going to be +2. Oops, sorry, wrong color. Oh, I swapped the colors here. Let me fix that. I did not mean to do that. I did not mean to swap colors. That's just going to confuse everyone if I do that. Okay. And this one should be green. And then finally, this last one, we only have carbon-oxygen bonds. This is going to be +1, +1, +1, +1. I think that was the right number of ones, but +1, +1, +1, +1. So we can see here that's going to be a +4 oxidation state. Okay? So we can see here that this first one has 1 carbon X bond and 3 carbon hydrogen bonds. The next one here has 2 carbon X bonds and 2 carbon hydrogen bonds. This one has 3 carbon X bonds and 1 carbon hydrogen bond. This one has 4 carbon X bonds and 0 carbon hydrogen bonds. And remember, the organic chemistry definition is as we get more hydrogens, more carbon hydrogen bonds or less carbon X bonds, that's going to be reduction and vice versa. Less carbon hydrogen bonds, more carbon X bonds, that's going to be oxidation. So we can see here that overall, moving to the left is going to be reduction. We can see our oxidation state getting lower and lower. We can see our carbon-hydrogen bonds getting higher and higher, and our CX bonds getting lower and lower. That is reduction. We can see going to the right is going to be oxidation. Our oxidation states are getting higher and higher. That's why it's called an oxidation state, because the more of the state you get, the more oxidized you are. Our carbon X bonds are going up, and our carbon-hydrogen bonds are going down. So that is where the definition of oxidation and reduction come from. Are there any questions on that? Does everybody get it now? Okay.
So reduction is like decreasing in electrons?
Yes. Well, no. Reduction is increasing in electron density. It's decreasing the oxidation state. So if you think about it, remember, the carbon-hydrogen bonds mean that the carbon is getting more electrons. It's becoming more electron rich, so it's going to be more negative. You're gaining electrons when you do reduction. Does that answer your question?
Okay.
Okay.
Yeah, kind of.
Okay. Does anybody have any more questions about this? Okay, awesome. Okay, so let's take our different functional groups as examples. So let's say we start with a primary alcohol, which they can then turn into an, let me draw this right, an aldehyde. So this has do the oxidation state for me, and we will come back to that. Then this can become a carboxylic acid. So if we look at the oxidation states, we can see that the carboxylic acid is going to have an oxidation state of +3. This one here is going to have an oxidation state of +2. And this one here is going to have an oxidation state of -1. Okay? Remember, the carbon-carbon bonds count as 0. So we have, let me use a different color. We have 2 carbon-hydrogen bonds right here, which will be -1, -1. Then we have this 1 carbon-oxygen bond, which will be +1, which then turned out to be -1. And we did that for every single one of these. Sorry, this shouldn't be +2, this should be +1. That's what I get for doing math in my head. All right. But we can see here, as we're moving to the right, we're becoming more oxidized. And as we move to the left, we're becoming more reduced. There are certain reagents that can reduce and that can oxidize. So you can sort of think of these as different series of steps. So this is going to be 1 step, and this will be 2 steps. There are some oxidizers, some oxidizing agents that can go throughout both steps, whereas some of them will only undergo the first step. Okay? Does that make sense to everybody? Okay. So one of the ones that can only undergo 1 step is going to be PCC. PCC is only going to take 1 step, and it's going to stop here at the aldehyde. It's going to stop, and it's going to create that aldehyde, and it's not going to go forward to the carboxylic acid. However, most things with chromium, so K2, the one that you'll see most often is going to be K2Cr2O7. This will go all the way through both steps to that carboxylic acid. Okay?
I have a quick question.
Go ahead.
So what's the difference between PCC and like anything? Because I know what chromium does. I know if it has chromium, I know what's going to happen. But like, what makes it different than PCC?
So PCC stands for pyridium chlorochromate. So let's draw that really quickly. So, oops, sorry. Let me draw that a little bit better for you guys. You won't understand the circle. The circle basically means it's fully conjugated, but that's stuff you talk about in Orgo too. So we won't worry about that right now. So this is pyridium, and then we have chlorochromate. So essentially what's going to happen here is that when we oxidize once, when we get rid of one of these oxygens, this nitrogen will come in and complex with that chlorochromate very, very quickly, and not allow the reaction to proceed past that aldehyde step. Does that make sense?
Yes, ma'am.
Okay, awesome. So both of these do have chromium. Yes, you're correct. It's just if you see chromium by itself with nothing to sort of stop it from oxidizing all the way to the carboxylic acid, that's when it's strong. Okay? One other thing to consider is whenever we have a secondary alcohol. What if we have something like this? Well, we can only oxidize or reduce once because we can't get rid of carbon-carbon bonds when we are doing oxidation. We only get rid of carbon-hydrogen bonds. If we got rid of carbon-carbon bonds, then that would be like a completely different reaction. So no matter what, going from a secondary alcohol to a ketone, that's as far as it will be able to go. So you can either use PCC or potassium chromate. Either one will work because this is only going to be one step. You don't have a second step to turn it into a carboxylic acid. Okay? Does that make sense to everybody? Okay, awesome. So that is the general idea for oxidation. You will look more into reduction as far as organic chemistry 2 goes. But I think for this class, all you really need to know is how to reduce all the way backwards. So just like strong oxidizing agents, we can have a strong reducing agent. And that one is going to be called lithium aluminum hydride. This is going to be your strong reducing agent. And whenever you need to reduce something all the way, you'll be using lithium aluminum hydride. We don't really talk about weak reducing agents, but I can tell you that a weak reducing agent that would be similar to lithium aluminum hydride would be something called diisobutyl aluminum hydride. So that would look like this. You can see an immediate difference between LiAlH4 and DBA, as this is called. Because DBA is much more sterically hindered, it can only really release one hydrogen at a time. So this will only reduce one step. Okay? But again, what's more important in this class is the oxidation using PCC or the potassium chromate stuff. This isn't as important, but I did want to touch on it. NaBH4 is used differently. I would yes, if it's the only possible answer for a weak reducing agent, you'll have to pick it. But it's more selective than it is weak for reasons you'll see in organic chemistry too. But for right now, lithium aluminum hydride is going to be the main one. So PCC can be used for any, and then the chromium can be used for carboxylic acids. So let me erase this really quickly. So again, PCC reduces one step, and then the chromium reduces 2 steps. But when we have a secondary alcohol like this, we can only only oxidize one step, We cannot oxidize any more than that because we can't get rid of carbons. So that means, yes, we can use PCC or chromium. Let me see the question again. PCC can be used for anything like K2. Yes, okay. So most of the time, you'll be using K2CR2O7 to oxidize all the way to a carboxylic acid, where PCC will be used if you only want to reduce once. I mean, I keep mixing up reduce and oxidize. I meant oxidize once, okay? Okay. All right, so LiAlH4 can't be, no, LiAlH4, that can be used to reduce anything. If you want to reduce anything to a primary or a secondary alcohol, you can just put in LiAlH4 and it will reduce it. It can reduce anything. It's very, very strong like that. Okay? And by reduce anything, I mean reduce oxygen bonds. rather than double bonds. Double bonds is a little bit of a different story. And we talked about reducing double bonds when we talked about H2. Oh, LiAlH4 will not stop at aldehydes. It will go all the way to that primary alcohol. Okay? Again, you don't really need to know the reducing as much as you do the oxidizing, but I do want you to know that there are sort of counterparts to the oxidizing, the strong oxidizing reagents and the weak oxidizing reagents. So why would K2Cr2O7 be used for secondary if it cannot go to the aldehyde? Well, you don't really need to, like, PCC and the K2Cr2O7, they'll do the same thing. It's just up to personal preference which one you use. I don't really want you to worry about NaBH4. That's not something I want you to worry about right now. Okay? Okay, so that is overall oxidation. And no, I don't think you need to know the mechanism. I will talk briefly about the lithium aluminum hydride mechanism when we talk about Grignard's reagent, but not right now, okay? That is the general idea of oxidation and reduction in reference to carbon-oxygen and carbon-hydrogen bonds, okay? Does anybody have any questions? I know this is a intense sort of question here, but I just want to make sure everybody's understanding this. Okay, so let's quickly do an example. I think this is from the PowerPoint. I think I remember doing this in the PowerPoint, but let's classify this reaction. Is this going to be oxidation, reduction, or neither? And oops, sorry, there shouldn't be a double bond there. That should just be that. So will this be oxidation, reduction, or neither? So when you're being asked that question, whether it's oxidation, reduction, or neither, you have to take into account all carbons, not just one carbon, because one of these carbons could be reduced and the other be oxidized, okay? So try and answer this. I'll let you guys have some time to do it. If you're watching on YouTube, pause the video and try to answer yourself. All right, so the answer for this question is going to be neither, okay? So let me explain why. So the way that you answer these questions is you're going to sort of focus on which carbons are changing. Oops, let me use different colors. So we can see that this carbon changed and this carbon changed. But I'm a little sneaky here because I didn't draw on the hydrogen because, as we all know, organic chemists are really lazy and they don't draw on the hydrogens. But just because it's not drawn in doesn't mean it's not there. So if we look at the pink hydrogen, so let me just pink hydrogen, we can see that the oxidation state over here we had this, so that means it was -1. But then the oxidation state over here is going to look something like this. So we have -1 plus 1, it's going to be 0. So we went from -1 to 0, that's going to be reduction by 1 degree. So we did 1 reduction. So I'm going to say 1 R. When we look at the green carbon, however, when we look at that, we will see that we start with the same thing, something that looks like this. We start with -1, and then we end up with this. Oh, I'm sorry. I said this is reduction. I meant to say this is oxidation. Sorry. I was getting caught up with the next one. But this first one is oxidation. So we're going to say it's 1 oxidation. We can say here we went from -1 to -2. This is a reduction. We reduced by 1 degree, so this is 1 reduction. We can see we reduced by the same amount we oxidized. So they cancel out, and this is going to be neither. Okay? Does that make sense? Does anybody have any questions about that? Okay. Again, you have to look at the whole molecule and not just the individual carbons, which can be a little bit difficult the first time you do it. All right, and I think that is alcohols, just in general. Does anybody have any questions about that? We're going to talk about Grignard's at the very end. We're going to come back to it. but we are done with alcohols right now. All right. Okay. So the next thing we're going to talk about is ethers. I'm going to skip over nomenclature because we've already been going for an hour and a half, and my voice is starting to give out. So we're going to sort of skip over nomenclature because I feel like you guys can figure that out on your own. And let's talk about the actual reactions, how we make an ether. So there are a few ways that we can make ethers. My personal, I guess, favorite is going to be the Williamson ether synthesis. And the reason why it's my favorite is because it is pretty easy. So Williamson ether synthesis, we start out with whatever ether we have right here. And we say, all right, how do I want to make this ether? And the way that you do this is you sort of cut the ether in half at the oxygen, and you redraw each half twice. So 1, 2, and then 1, 2. All right. So one half you're going to give the oxygen, and the other half you'll give some sort of halogen, bromine. You're going to do the opposite with the other two pairs. So we put oxygen over here and bromine over here. So when these two react as if it were an SN2 reaction, so these two will react together as SN2, they will come together to make this ether. That is all Williamson ether synthesis is. But what we have to do with Williamson ether synthesis is we sort of have to consider which one is going to be the better Williamson ether synthesis. And the general rule of thumb is that the one with the less substituted alkyl halide will be the better choice for Williamson ether synthesis. So that means that this one up here is going to be the one that is preferred when we do our reaction, whereas the one on the bottom is not going to be preferred. So in summary, we want to give the less substituted half the halogen. Okay? All right. So let me read through these questions really quickly. All right. So the actual reaction for this is going to look something like we start with an alcohol. We start with this alcohol, and then what are we going to do? We are generally going to want to deprotonate it somehow. And what we'll do there is we'll use NaH, because again, if you remember, NaH is a really strong base. So it's going to deprotonate that oxygen, and we end up with this O negative right here. So that's when we're going to be using NaH. All right. And then that we will react with the alkyl halide. Okay. Does that make sense to everybody? The least substitute is the major. Okay. So when we talk about Williamson ether synthesis, the ether is the product. When we are looking at these as potential reactants. For using NaOH, that's going to come in a little bit later, specifically when we talk about Oxiranes Aka Epoxides. We'll talk about NaOH a lot more, but generally here we're going to be using NaH more to deprotonate this alcohol into this oxy right here. This I guess this would be 2-propoxy. Okay. Okay. And so then this 2-propoxy will then react with bromine. The mechanism here would essentially be, oh, there's my dog. Everybody say hello to my dog. This hydrogen will have extra electrons. It'll come in, grab the hydrogen right here. This bond will break, and we end up with O negative, which then is going to come over here and replace the bromine on the carbon. And we finally end up with our ether. Okay? Does that make sense to everybody? Okay. So some people were asking when to use NaOH versus NaH in this case. When we're doing Williamson ether synthesis or any ether synthesis, basically, we're going to be using NaH over NaOH. when you guys are asking about using NaOH versus NaH, you're talking about cutting the ether in half. And while I did say we're going to cut this ether in half up here, I was talking about cutting this product ether in half to find the reactants. When you're starting with an ether and ending with these, then you have to choose between those. Right now, we're talking about starting with the alcohol and the alkyl halide and ending with the ether. Okay? Does that clear up that question for everybody? Okay. So, okay. So that overall is the Williamson ether synthesis. But we can use a couple different strategies in order to do this to create more ethers. The Williamson ether synthesis, I like it because it just shows you a little bit of everything. But there are a few other ways that we can do create an ether. One of the ways is to use two identical alcohols and react them with a strong acid such as H2SO4. An example in the PowerPoint is using two of these alcohols along with H2SO4 to make a ether. And the reaction here that's occurring is basically the H2SO4 is going to donate one of its hydrogens to one of the oxygens, just like when we were doing acid catalyzed dehydration. So let me draw this HOSO3H. So the oxygen grabs onto the hydrogen, this bond breaks. We end up with OH2 plus OSO3H negative. And then this will go along and it will react with the other OH, the other alcohol, which will go in, replace the OH2 on the carbon, and we end up with something that looks like this, which then is deprotonated by that OSO3, and we end up
confused. Sorry, where is the other alcohol coming from?
We started out with two of them.
Oh, I see that. My bad. I'm so sorry.
You're good. You're good. It's just only one of them ends up being protonated, which then is replaced using this alcohol right there, which then we finally deprotonate using this base right here. So you can see a lot of these reactions follow very similar steps. It's just we're shuffling them in different ways. This reaction is the preparation of an ether from an alcohol using the strong acid. It's not called anything specific. I think in the list it's called preparation of ether from alcohols because there's no alkyl halide used in this reaction. Okay. All right. Is this constant? It doesn't really matter. Dilute acid, concentrate acid. As long as you see the acid, then it should work. Okay. So next, let's talk about the actual reactions that it can occur with. So I'm going to go ahead and clear this. So let's say that we have let's use that same ether that we had in the beginning, an ether that looks like this. We can react this ether with different things in order to create, I guess, like a new product. And this is where using NaOH versus NaH is going to come in. But first, we're going to talk about just the general acidic cleavage of an ether. We start out with an acid. Usually this is going to be something like Hbr or Hi, one of the two. And what'll happen is it's first going to protonate that oxygen, just like we did before when we talked about the replacement reaction of an alcohol. We're going to protonate it like this, and we end up with, oops, that's pink, not black. We end up with this right here, positively charged, this right here, this. And so, of course, we can treat that as a good leaving group, and the leaving group will leave. What's important to note is that this is going to leave from the more substituted carbon. So technically, there are two ways that we can lose this OH group. We can either lose it like this, or we can lose it like this. Yeah. This one on the left is going to be preferred because we create the more substituted carbocation. So what will happen is, let me get my eraser. That leaving group will leave. We end up with this carbocation plus this alcohol right here. The carbocation is attacked by that residual Br. And then we have cleaved the ether into two, an alcohol and a alkyl halide. We can also further turn this alcohol into an alkyl halide by reacting it with Hbr, which will then follow the same mechanism that we talked about before with alcohols, and we end up with this right here, okay? So our overall two products would be these two alkyl halides. But if we only reacted with one equivalent of acid, then we would end up with these two as our products. It just depends on how much acid we're reacting with. Okay, so what's important here to see is to see how we lost this OH group, which side it lost, which side it left as a leaving group. Because we can see here, it left from this side as a leaving group rather than the other side. If we decided to react with a strong, like a base or something with an OH instead of an H, then we would do the opposite, okay? So one example that somebody has sent me, and since the homework is already passed, would be this one right here. Okay. Oh, sorry, I drew it wrong. It should look like this. Okay. Okay, so when we look at this and we want to cleave this somehow, we can cleave this in a couple different ways. We can go with route 1, where we end up with our oxygen on the left, and then some sort of halogen, some sort of alkyl halide on the right. I'm just going to say Br, because Br is all reliable. We can also undergo the other route, where we end up having our Br, or our halogen, on the other side, and our OH over here. So this basically is all going to depend on whether you're going to be using a hydrogen or if you're going to be using a base. Like we said before, when we're using H+, we are going to break off the oxygen from the more substituted version. So let's go ahead and draw that out. H+. We end up with this. Obviously, this side is going to be more substituted. So we are going to lose the oxygen from that side, and we end up with our carbocation plus our alcohol over here. And so then we can see, obviously, this is going to go with the second route, okay? And if we use the base, then we'll do the exact opposite, okay? Does that help clear up those questions that you had about NaOH versus NaH? So like the second pathway here would be using NaH. This first one would be NaOH. Okay? Does that make sense to everybody? All right, and I think that is the main stuff with ethers. So now we're going to go on to Oxiranes, aka epoxides. So epoxides, Oxiranes, those are just fancy names for if we have an oxygen as part of a cyclic compound. Most of the time, you'll see them looking like this, and this is usually the easier form, okay? So if you remember from back in the previous tests, whenever we had a double bond, we could react that with a peroxy acid, usually MCPBA. And what will happen is that will magically turn this into an epoxide. I went over the mechanism back when we talked about MCPBA, so I'm not going to go over it now. And again, you can go watch those videos and you can go see those again. Okay? All right. So that's the main preparation that we've gone through. We can also make these epoxides using halohydrins. If you don't remember halohydrins, basically all that means is we have an OH right here and a Br right here. Okay? And so essentially what's going to happen with these halohydrins, the bromine is going to act as a leaving group. It leaves. We end up with this right here. And then the oxygen on the OH will act as a nucleophile, go and grab onto that carbon. We end up with this right here. And finally, it is deprotonated into our final epoxide. So those are the two main ways of making oxiranes or epoxides. One is up here where we have a double bond, and another is right down here where we have a halohydrin. But there's only two real ways that we know of, so we don't have to worry about that too much. Okay? Okay. So what prompts the halogen to leave? I mean, it just kind of leaves for the same reason. Remember when we're doing SN1, it just kind of leaves. Like there's no set reason. It's just a good leaving group. So it leaves, that's its job. Okay? And those are the two ways that we make an oxirane. All right. So let's talk about the reaction with oxirane. And let's specifically talk about the reaction of an oxirane, including the stereochemistry. So let's say that we have something that looks like this. Actually, let's have something that looks like this. So it's the same on both sides. Okay? So is everybody with me with drawing this? Does everybody understand how we've drawn this in this way? Okay. So, so what we will do is essentially we're going to have this here, and then we are going to break the epoxide and add something to it. We're going to add something to it by essentially either protonating the oxygen first or protonating the oxygen second. Let's first start with something more familiar. Let's start with the nucleophilic attack. So let's say that we have OCH3, O negative CH3. What will happen is it will come in, it will attack one of these carbons, this oxygen will leave. This is going to occur basically by an SN2 mechanism. And so then we end up with this. Okay, and let's pause for a second here. And let's note that the O negative and the OCH3, our nucleophile, are on opposite sides of the carbons. This is because this OCH3 is sort of pushing on the oxygen. It wants to stay as far away from the oxygen as possible as it's adding on. So it adds on to the opposite side. It's a backside attack because similar to an SN2 reaction is a backside attack. Okay? Does that make sense for everybody? And after that, we're going to protonate it. We're going to add on a hydrogen, whether it be from water, H3O+, H2SO4. Usually it'll be water, but what'll happen is then we'll protonate and we end up with our final product. OCH3, oxygen right here. Hold on, let me pause real quick. So we can see that the wedge is going to stay right here. We can see that it adds to the opposite side. So let's look at this stereochemistry really quickly. So let's look here, here, and here, just highlighting things with the same thing. And I don't know how much longer this is going to go on. I don't know how much longer my voice is going to, keep going, but we're going to do our best. But yeah. So we can see this oxygen will be 1 because oxygen is going to be that highest priority. Same over here. And then we're going to say, oh, there. Okay, so then we're going to say that this is going to be 2 and this is going to be 3. Same over here. You can see that the blue becomes 1, 2, 3. That is going to be S. The green is going to be 1, 2, 3. That's going to be R. We can see over here 1, 2, 3. R. 1, 2, 3. R. So you can see here that the stereochemistry is flipping. So this one's going to stay R. Nothing really changed there. Same here. Okay. So you can see that the stereochemistry flipped because we attacked through a backside attack. Okay. Does that make sense to everybody? Does that answer your question? Okay. So when we're talking about substitution, or not a substitution, but nucleophilic substitution, a nucleophilic ring opening, we can see that we attack first and then we protonate second. When we're using an acid, we will do the exact opposite. We will protonate first and then attack second. So acid catalyzed opening. So we can see here that the hydrogen is going to get grabbed by the oxygen, and then we end up with OH+. And then here and here. And then we will attack with our nucleophile. Usually we will be attacking with a weak nucleophile. So instead of OCH3 would be HOCH3. It will then attack. This one will leave. We again end up with an inversion of stereochemistry. And we're also going to have to basically deprotonate, get rid of that hydrogen, and then we end up with this same product. The times that we will end up with different products is when we have different amounts of substitution on an oxirane. So I'm going to clear this, and we're going to show the two different types of reactions when using an oxirane with different substituents. So we'll have this here, and let's say that this one has 1, 2 substituents, and this one only has 1. Okay, so let me move this to the side. I'll move this over here. So there are 2 ways that we can attack this. We can attack this one first with a strong nucleophile, so OCH3 negative. So remember, this is going to be an SN2-like reaction. It's not SN2, it's not exactly the same, but it's similar enough that we can say, remember when we talked about SN2, we wanted to attack the less substituted alkyl halide. The same thing is going to occur here. This OCH3 is going to want to attack the less substituted carbon, aka the carbon on the right. And then we'll break off here, and then we will go on, follow it up by a protonation, and then we will end up with this here. OCH3, oops, this right here, okay? However, if we protonate first, so let me use a different color, so we're gonna have H+ first. If we protonate first, it's gonna grab onto the hydrogen, and we end up with this guy right here. Okay, and so we are going to end up attacking the more substituted carbon because of the 2 different transition states. So we're going to have our nucleophile, and we're either going to attack at this carbon or this carbon. When we attack at that right carbon, we're going to end up with this transition state. H, with a partial positive on this oxygen, a partial positive on this carbon, and a partial positive on whatever our nucleophile is, which is going to be our H2 or HOCH3, but we will do it in a second. So we end up like this. If we attack at that other carbon, then we will end up with this transition state. Oops. And if you remember, we talked about this a little bit before in previous chapters, that the transition state with the partial positive charge on the more substituted carbon will be more stable. Okay? Which means that we are not going to use this transition state, and instead we will use this bottom one. And again, we are going to invert stereochemistry over here. We're going to end up having OCH3 after the deprotonation here, here, and here. And no, we are not inverting this right here, because basically what happens is the nucleophile pushes up that methyl group in the same position as it was before. And it's going to have an inverted stereochemistry, so it's going to have a different R or S configuration. Same thing here, but these methyl groups are the same, so we don't really worry about it too much. But we can see here that when we protonate first, when we are acid catalyzed, we are going to add to the more substituted carbon, whereas up here, where we attack first, when we do our nucleophilic attack first, then we will end up being added to the less substituted carbon. Okay? Does that make sense to everybody? All right. All right, so I'm gonna go ahead and call it because I'm losing my voice a little bit. You probably heard me coughing, but I'm going to do my best tomorrow to upload a video about sulfides and thiols, just walking you through everything. And they are very similar to alcohols and ethers, so it shouldn't be so much of a stretch for you guys to learn about that. So yeah, I've hoped I helped. Again, message me if you have any other questions, and I will definitely answer them as soon as possible. Have a great day.